So can you hear me? Yeah? Yeah, so hi everyone. Oh, hi everyone. Let's try to document a little bit those not documented parts of the ESP32, in particular the Bluetooth part. And well, let's start with a little bit of context first. I am Anton. There you have my social media, because I will not have a steady place to be around in the Congress. I will be walking around. You can contact me in any of those places. Also, I work as part of the research and development team of a company back in Spain that's called Tarlogic Security. And we have been carrying out a long Bluetooth security research line that led to some discoveries early on that were particular. Some of you may already know, for example, Blue Spy, which was about listening to audio from earbuds. And because we found out that there was not that many documentation around, we decided to perform some standardization of that documentation, and we published a Creative Commons security assessment methodology, which you may know as BSAM. It's kind of the OWASP thing for Bluetooth, but we also realized that there's a lot of things that we can still improve to make Bluetooth security a little bit better. We are now working on tooling, because we have found out that there's a lot of things that are missing to really be able to carry out security checks on Bluetooth, and particularly, we are lacking an affordable way to access some low-level capabilities of Bluetooth hardware. And what do I mean by that? In Bluetooth, we have these two main architectural parts. One is the host, which would be your general-purpose hardware, such as, for example, your PC. And there's this chip we call controller that is really specialized and tries to access and tries to take care of time-sensitive operations, and it has these radio frequency capabilities to talk to other devices. And usually, we get control over the host part. That host part can talk to the controller through a standardized protocol that is called HCI, which limits our capabilities of controlling or taking the controller to do things that we would like to. But the reality is that most of the communication takes part on those lower layer parts. So a controller will talk to other controller, and we will not see it. So that's what we are missing now. When thinking about what hardware to do this on, we obviously had to look into the ESP32, because I think it's one of the most available chips out there. It's their chip, and also it is one of the few microcontrollers you can find around that can do Bluetooth Classic and Bluetooth Low Energy. On top of that, it is a good starting point for us, because the SDK is already quite open source. There's still a little, some source blobs that some closed source blobs that are Apache licensed. That's also a nice feature in the sense of that the license choosing allows us to reverse engineer and publish work that's derived from that reverse engineering. So now we will move on to the reversing part. First of all, the first steps would be to compile, to get all the public information we have on the chip. And Espressif publishes almost everything that, well, almost all that runs on the ESP32, and it does, they do publish more than they need to. So, for example, we can find the ESP32 ROMs and the Bluetooth and radio frequency libraries directly on the SDK, and those ROMs usually come with symbols inside. So That's really nice from Espressif, but because I will be doing the reverse engineering with Ghidra, reversing those libraries separately, it's kind of tedious because you can look into one, but it references the other one, so you have to go back and forth to understand what's happening. But we can join them into a golden binary. This has been done previously. We have done this using the linker tooling that's on the SDK. But if we set this minimal bit property to off, a standard ESP IDF project will do the same for us and will take care of linking everything as it should be. So we have created this small ESP IDF project that contains all the components that we are interested in, and it will generate a binary output file that contains all the symbols we need to reverse engineer. Just a warning of a caution, ESP IDF version will affect the output a lot because different versions of the lib have different functions and different information on them. So it will be nice if you compile this for different IDF versions. So yeah, this is the simple IDF project we have created. It just specifies the components that we want, and it says the trimming to off, and it will generate the golden binary. There are a couple of function names that are not or may not be in the output file, and those can be found out in a linker script that is also in the SDK. But because Ghidra cannot import that information automatically, I have built this Ghidra plugin that simply takes the linker scripts that are on the SDK that contains a function number and an address, and it loads all of that information into Ghidra and tags the name of the functions, whether they exist or not. The name will be tagged inside Ghidra. So this gives us a lot of context to reverse engineer and understand what's happening behind the obfuscated code. So there's this thing that the ELF binary only contains the memory map of the code and some portions of RAM that will be used. But the code we want to reverse engineer directly talks to peripheral memory, which is are regions that are mapped into the memory bus, but that they are not, they're referenced directly as addresses in the code. And there's a lot of information published about this in the datasheet, but because we're proper lazy, we found out that there's this SVD format, which contains the same peripheral information, but in a parsable format. So I wrote another Ghidra plugin. There was a previous SVD loading plugin around, written in Python. This one is Java and integrates in the user interface, but both of them should work perfectly. And we have two sources for SVD packs. So Espressif SVDs, they have an official repo where they have the files, but they're quite fairly updated. And the ESP Rust community team has taken those SVD files and built some patches on top of them that improve the quality of the SVD files a lot. So I would recommend to use the second one. This is the Ghidra plugin. It just file import SVD, and it will pop a window telling you, oh, I'm going to create all these memory sections for you with these properties. Are you OK with it or not? Now, we would have the full information that we want to look at, but we want to look at the missing bits. So what do I mean by that? The Bluetooth code talks to memory regions that we have not yet documented. So strangely, Ghidra does not have a way for you to look up all the places where the code is trying to reach memory that is not there. So again, I built another GitHub plugin. This one just does that. It's a fairly simple plugin. It has a list of functions that you will see on the right. And on the left column, it will tell you where those functions are trying to access, either by read, write, or data, whatever type of reference GitHub is trying to analyze. And as you can see on the left, we see a lot of functions that have the BT name on there. And all of those are trying to access 3FF71000 or plus some offset. So, yep, that's all the information there. Now, a lot of elbow grease and a lot of code reading. Context and usage of memory is key. So, looking into bitmask, function names, everything helps. There were also debug info line and file names. So sometimes even knowing where those pieces of code were originally in a file also helped. And there were some asserts string asserts that leaked some register naming. But after reading, not always enough. Reading is not always enough, and we needed to perform some tests. So we also built a lot of small firmware tests that read and write values to those memory regions. And we even went and designed some ESP32 boards that had a JTAG for us to be able to debug what was happening, and some SMA connectors to be able to connect or ESP devices to some specialized hardware that mostly was a cat sniffer from the Electronic Cats and a HackerF from Great Scott. And this is the setup. It was fairly simple. The PCB on the bottom is the ESP board we have made, connected to an attenuator. And up, you can see the cat sniffer. I live in a fairly radio frequency quiet place, so this was enough for me. But I also had these cheap isolation bags, RF shields, that also helped a little bit. If you're trying to do this in a city, I will for sure know that you will receive outside traffic no matter what you do. But yeah, for me that was quite enough. So now, let's move on to what we have found. This is my take on what I have found. Probably there are errors here, but I will try to explain what I found in the best way I can. We found out a fairly complex Bluetooth peripheral architecture. So on the left, in the middle, there's this Bluetooth dual mode core block that on the left talks to other peripherals that have like hidden buses that I don't think we can see. But we know they're talking in between for the Bluetooth to be able to send and receive messages via radio frequency. And then this core, this Bluetooth core, communicates with the main core via 3 main mechanisms. So there's an interrupt line, which the Bluetooth uses to notify the main core that something has happened or something needs to be handled. The core is able to read and write to some registers that are inside the peripheral. Those are for general configuration of the peripheral. And then the peripheral also has a memory controller inside that is able to read and write from RAM. That will be the main channel for exchanging information. Okay? So this Bluetooth dual mode core contains registers for configuration. As I said, most of this configuration would be enabling, disabling, some interrupt configuration, like I want to get notified of this, but not that, and sometimes some error reporting. If we screw up configuration with the exchange memory, we can see that kind of errors in the registers. There's also configuration for general options such as timing, clocks, and encryption. and we can configure the exchange memory from these registers, which are always in the same place. We have documented more than 40 registers, and we even have the fields for, I would not say all of those 20 registers, all the fields for all of those 20 registers, but there are 20 registers are really well documented. We have forked the ESP packs repo, and I have uploaded the patches for Bluetooth this morning, and I have opened a pull request to send those changes back upstream. So hopefully, if someone is seeing this, please look at that. Do not let it rot. And yeah, the second memory region we were talking about is this shared memory region. This shared RAM region that contains a lot of linked tables. This is quite a big region, okay? And each table handles some part of the Bluetooth information exchange with other devices. So, for example, there is a table that configures what each Bluetooth slot can or should do, like should the peripheral scan, should it advertise to other devices, should it connect or expect connections to be incoming. And there's also tables for frequency management and hop control of these communications. There's tables for transmission and reception buffers. So it will be something like this, where we have a lot of tables for frequency, encryption, control structures which manage which operation should take place, whitelisting, TX and RX description, and then after that, VR, EVR stuff, which is even bigger than what you're seeing. So we have this problem that is that both the Bluetooth core and the main core can access that RAM simultaneously, and both can modify that memory. And also we have a second problem, that is that all Bluetooth communication has some fine timing requirements. So there's this prefetch mechanism that handles these two problems and manages user interaction and timing requirements for communication. So at the beginning of the exchange memory, there's this 16 event slot table, and each of the slots is read and processed, synchronized to a 625 microseconds clock. Every 625 microseconds, one of these events will be processed, and just before processing it, the peripheral will try to get the information of the table from the exchange memory. So this is what we call the prefetch mechanism. So the way to work with this peripheral would be something like the user will prepare the required exchange memory information in RAM. Then the user will set a bit in one of those tables, and the peripheral will be looking around at the memory, and when it catches that pending slot, it will process the slot, do whatever operation the user has specified, and afterwards it will notify the main core via an interruption, and the user can read the resulting data, such as, for example, advertisements. Now, what can be done? So, easy answer. We can do everything that should be done. So all the standard procedures, so the hardware is documented enough to be able to perform the standard procedures of Bluetooth, such as scanning, advertisement, connection, and awaiting connections. But we also documented a couple of modes more, some RF radio frequency testing modes, which allow us to transmit continuously and receive continuously. And the thing is that we can do all of those operations, but with low-level access. So some things that we can do with this is, for example, log all the low-level radio frequency traffic to see if everything is compliant, or even if there's some unexpected traffic. We can perform per-channel scanning, which previously was not possible in the ESP. Now we can set a particular channel to scan on. And we can also transmit arbitrary radio frequency traffic with the Bluetooth peripheral. Such as in other projects, we will be able to follow and sniff connections that we can see happening. So for example, if we see a connection packet start, we can take the parameters from the connection and just follow that connection and dump the traffic. And there's this mechanism which allows us to receive packets with a certain level of bit error on them. So we could theoretically receive some traffic of which we do not know the synchronization word which will be in this connection packet. So a partial sniffing can be made. Also, because of the RF modes, we could continually jump one single channel. This is very helpful if we want to perform some kind of Bluetooth attacks in the real world, because, for example, we can force one channel to not be used, and then we know, for example, that that traffic can be in another advertisement channel and listen to those other advertisement channels. This is also useful because sometimes, in order to implement some attacks, we do not want only the access to the low-level traffic, but we want a normally working Bluetooth controller. And we just want to modify one specific behavior. So we have the full implementation. We have the reverse engineered registers. We know what's happening. And maybe in a certain point, we can patch something and do the thing work as we want instead of the standard way. Also, because of the arbitrary sending and receiving things, we can do low-level protocol fuzzing, which was previously not possible with the ESP. Unfortunately, originally, we wanted to build a full monitor mode sniffer, but unfortunately, all those Bluetooth packets have a series of, they have a synchronization word, which is a preamble to the packet, and that is not known for connections in general. So we cannot build a full monitor mode with our ESP device. And I am not sure that we can obtain all Bluetooth packets from this peripheral. There may be some packets that are handled internally and not even sent up to the user. So a little bit of conclusions for this. So there's enough documentation to start working on an open source controller stack, or at least to understand whatever is happening in the current stack. And there's a lot of documentation, and it's enough for tinkering and implementing custom tools and proof of concepts. Writing an open source controller stack would be too much for a single person. So I think I will not be starting that. But for sure, I will try to push and upstream all what I have found to the official ESP repositories. And there's also another thing that, well, it interests me a little bit more, which would be to go down to the other peripherals, such as the modem and the radio frequency physical peripheral, to see what's happening there, and if there's something else to get out of the ESP32. So, for reference, for those of you that are into reverse engineering, here you have the link to the repos of the Ghidra plugins I've made. And for the ones that want to see the Bluetooth part, there will be, well, the pull request is already going. So, yeah. Official, well, community ESP Rust Packs repo has gotten a pull request with the registers documented. There will be some blog posts about the process and the findings we have looked for, and there will be another repository that will contain all the detailed information on the exchange memory, how to operate this peripheral, and the details on how this works in fine detail. Yeah. Finally, I want to thank Tarlogic for allowing me to do this in paid work hours, which they have been very patient with, and especially to my colleague Isaac Lleida for helping me in those reverse engineering valleys that always take place. I want to thank Espressif for the SDK and for open sourcing part of their SDK and for the license choices that they have made when they did not open source it. Frosty and Jasper, because they started all of this last year by opening the Wi-Fi of the ESP, and now, yeah, I had to follow. And of course, thank you everyone for listening.
Thank you very much, Anton, for this liberating talk. Thank you very much for that. I'm still looking at my device, whether it's already been hacked or not. Are there questions for Anton? Please, microphone number 3.
Hi. Thank you for your presentation and for your work. Awesome. And I wanted to ask, on this level you were able to go to what kind of channel state information about like signals phase and so on were you able to cover, if any?
Oh, so you mean like CSI in Wi-Fi?
Yeah, I don't know what's the equivalent in Bluetooth, but...
For Bluetooth lower than 6.0, there's no ranging information available, as far as I know. That's kind of a new feature in Bluetooth that the ESP, I don't think, supports. So I have found information about channel. Sometimes they advertise transmission power, and I can get the reception power, so I can range, or I can model the distance to a transmitting device. But there's no phase information as far as I know in this device.
Okay, thank you.
You're welcome.
This is microphone number 5.
Do you have any information on how the BTDM's firmware is loaded so that we can start reverse engineering the next layer down the cake?
So the BTDM firmware there's no BTDM firmware. The architecture is, the peripheral is, I think, mostly implemented in some kind of Verilog or VHDL, and then VLSI and into metal. The peripheral only handles certain aspects of the communication, and then it sends everything to the main core to handle. So the firmware related to the peripheral is in the main core, and you can find it in the Bluetooth library and the ESP-ROM. So there's nothing hidden there. You can use the Golden Binary project that I have uploaded to the ESP reversing repo, and you can look for all the code that's being executed there. It is quite a mess. If you're going to go down that rabbit hole, I recommend you to write me, because there's a whole new real-time operative system there on top of FreeRTOS. So there's 2 real-time operative systems running in the ESP, and one of that is from the peripheral manufacturer, which I believe is Riviera Waves, but I cannot confirm that. Yep.
Thank you very much for this question. Number 4, please.
Yeah, hi again. Thank you for your work. I just want to understand that this is the digital part that you have covered, right?
Yep.
After it is digital, it would be somehow converted into analog or RF and then be sent outside, right, through the transmitter or receiver. So maybe this is the PHY that you talked about, or So I just want to understand, what do you see is the next part? How can somebody reverse engineer, or if it's possible to reverse engineer this analog and this analog to digital conversion or digital to analog conversion?
Yeah, that's definitely the part I would like to look at after this. There's definitely some information to be published around that. As far as I know, there's an internal I2C bus that is in charge of configuring that radio frequency peripheral and possibly a modem. I don't know. I would have to look into that. But as far as I know, because of the chip architecture, the process of reversing those peripherals should be the same work I have done, but instead of looking at Bluetooth functions, you should look for phi functions, physical. I've seen a lot of functions that start with phy, which should be the ones related to this peripheral. So the workflow should be the same. You can import the new information I have found, and then look for code that talks to memory that's not mapped, and that has the phi in the number.
Okay, great. Thank you for the answer.
Thank you very much.
Microphone number 6, please.
Hi, thanks. You slightly talked about the next steps and the fact that building a Bluetooth stack is kind of difficult. Did you check out the Zephyr link layer that was contributed by Nordic?
Yeah.
I know it's kind of hard to work with, but it works.
Yeah, I've seen that. So in Bluetooth world, there's not a lot of there's a lot of private implementations for controllers, but the only I know that is open source is the one you have mentioned, the Zephyr one. The problem is it is only for low energy. This one is for both. So that's the main reason to go this painful way, but hopefully it will allow us to do some more things that previously were a little bit hidden. But yeah, it's a nice way to start looking into this, because I would say that controller implementation would be on the tens of thousands of lines. So it is not nice work to start.
Thank you. Number 3, please. Microphone 3.
Hi, does the phase shift keying file of Bluetooth use differential phase shift keying or normal phase shift keying?
Hi, Frosty. Please, a round of applause, because he was one of the guys that made me start this. Yeah, so yeah, phase shift key. I don't know almost anything about what's in the radio frequency part of this device. Maybe we will have to sit down and look at both of us and see if we can come up with an answer.
Okay, great talk, by the way.
Thank you very much.
And microphone number 1, please.
You mentioned in your talk that you can now transmit arbitrary BT/RF. Is that only for validly constructed frames, or are you able to kind of fuzz implementations by constructing invalid frames?
Yeah, there are some limitations, but I think we can get around them. So the thing is that the memory structures have to have some kind of meaning. So there are fields you cannot change, but the RF transmission test mode allows you to send an infinitely long packet. So if you're careful enough, you can craft a packet inside a packet, and then in the middle of the packet you have sent, then send whatever messy thing you want to get out in the air. So I believe it can be done. I don't think it is fairly easy, but I would say yes.
Thank you.
Thank you very much.
Okay, thank you very much, Anton. Have a great applause from this wonderful crowd. Thank you very much.